Ahoy! We recently learned about the product rule, which allowed us to take the derivative of a product of functions, a function that was made from a product of smaller functions. Today we're going to learn the quotient rule, which allows us to take the derivative of a function that is represented by a quotient of other functions. For example, we might want to differentiate a function, let's just go with y actually. Y equals 5x minus 1 over x plus 1. This is a function that is clearly a quotient, and so we need a quotient rule, which I'm going to share right now. Bam! Let me read it to you, and then we're going to talk about it a little bit. So we've got the quotient rule, and it says that if we are differentiating a quotient, f of x divided by g of x, then our answer is also going to be a quotient. The denominator is not that complicated. The denominator is just the denominator of the starting function squared. The numerator, though, is going to be the bottom function times the derivative of the top minus the top function times the derivative of the bottom. And we have our simpler notation here as well. If we've got the derivative of a quotient, we've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. There is a mnemonic that some people will use to try and remember the numerator here. So if we call the two functions the high function and the low function, instead of the numerator and denominator or the top and the bottom, if we call these high and low, and I'm just going to write HI and LO just to write less. The way that we can look at the numerator is G is that lower function, so we've got the lower function times the derivative of the higher function. We're going to call that d high, derivative of the higher function, and then minus f is the higher function, so high times the derivative of g is the derivative of the lower function, so d low. And this might seem like it's not at all helpful until you say it all out. Low d high minus high d low. Low d high d low, with a minus in between. All over low squared. This is not something that I ever learned when I was first learning calculus. This is something that I have seen some instructors and TAs use. It's just a slightly easier way to maybe remember them, because it is easy to get them confused. With the product rule, if we forgot which one was the derivative of the first versus the second, yada yada, the order didn't matter because they were being added. But here, they're being subtracted. So if we were to switch these two terms, we would end up getting the opposite of the answer that we want. So that's why there's this little mnemonic, low d high minus high d low, all over low squared. Now, I'm not going to derive the quotient rule from scratch like we did for the product rule. For a few reasons. One, you can Google it or look it up on YouTube. I'm sure there are dozens of websites that do this already. Also, it is very similar to the product rule, so you could attempt it yourself if you are an advanced student and you want a challenge, but recognize that doing it from scratch can be quite challenging. You're going to use the limit definition just like you did for the product rule, but we end up with more complicated things because when we evaluate our function at x plus h, we don't get a product of functions with x plus h, we get a quotient of functions with x plus h. So we get a little bit more going on. It's a little bit more complicated algebraically. We do still do the trick where we find the right type of zero, the right version of zero to add so that we can break everything up in the appropriate way. But we're not going to do that now. If you want to do that, give it a try. If you want to talk about it in office hours, by all means come during office hours and we'll gladly go through it together. But for now, I just want to focus on doing the quotient rule because it is a little bit more complicated than the product rule, and so we want to get a good amount of practice here. So let's look at how we can use the quotient rule to differentiate this function y equals 5x minus 1 over x plus 1. So if we want the derivative here, dy over dx, we need to use the quotient rule, and so we're going to have a big quotient, and we've got to start with low d high and then minus high d low. So low d high means we take the low function, which is x plus 1, times the derivative of the high function. What's the derivative of 5x minus 1? Well, the derivative of 5x is 5, and the derivative of a constant is 0. So we just end up with 5 there. So that's low d high. And then we have minus high d low. The high function is 5x minus 1, and then times the derivative of the lower function, that's d low. The derivative of x plus 1 is just 1, because the derivative of x is 1, and the derivative of 1 is a constant. And then this is all over low squared, so we're always going to have to take the denominator and square it in the bottom. All right, let's go through the top and let's distribute things so we can simplify. If we distribute this 5 into the first set of parentheses, that's going to give us 5x plus 5. And then anything times 1 is itself, so we can ignore the 1, but we do need to distribute that subtraction in. So that's going to give us minus 5x and then plus 1, because subtracting a negative is the same as adding, all over x plus 1 squared. And there is something that we can cancel. 5x and negative 5x cancel. If we combine those like terms in the top, 5 plus 1 is 6. And we end up with 6 over x plus 1 squared, which is our derivative, dy over dx. So we have used the quotient rule to get the derivative. And one thing that's interesting to notice here, this derivative is always going to be positive when it's defined, because the numerator is always positive and the denominator is always positive or 0. So it's undefined when x equals negative 1, but that's when the original function is undefined anyways. So on the domain of our function, the derivative is always positive. What does that mean for our function? It means that it's always increasing. So the graph of our function is always going to be increasing. Now I want to do one more thing before we finish. When we were looking at the product rule, we asked ourselves when we were figuring out what the product rule might be, could it be super simple in that the derivative of a product was just the product of the derivatives? And we found out that that wasn't true. And I want to show you that the same thing happens when we try and look at quotients. So we might want to ask ourselves, is it true if we take the derivative of a quotient of two functions, f of x over g of x, is it possible that that's just equal to the derivative of the numerator divided by the derivative of the denominator? And just by picking example functions, we can see that this doesn't work out. For example, we could look at f of x equals x to the 8th and g of x equals x squared. Now, we know that if we differentiate x to the 8th over x squared, well, we know that x to the 8th over x squared is just x to the 6th. So we need to take the derivative of x to the 6th, and that's going to be 6x to the 5th. Let's look at what happens when instead we look at the derivative of the numerator over the derivative of the denominator. Let's see if that gives us the same thing. Well, so the numerator is x to the 8th. The derivative of that is 8x to the 7th. And the denominator is x squared. The derivative of that is 2x. 8 divided by 2 is 4. And x to the 7th divided by x is x to the 6th. Do we end up with the same answer? Well, we can see very easily these are not equal to each other. So when we take the correct derivative of this quotient, in this case by simplifying the quotient, we get a different answer than what we get if we tried to differentiate the numerator and the denominator separately. So that shows us that it's not so simple that we can just differentiate the top and bottom. That's actually why we have to develop a quotient rule, which is exactly what we have up here.